moving on, I have another result in the form of a theorem. So this example is done here. I move on to the next result. So, I have the result in this form. So, if I am given f and f prime and these are piecewise continuous, okay, and in this limit, in this range x from -1 to 1, and I am given that R inverse, I define my function h as follows: R inverse f is h, and I am also given that f of 0 is given to be this integral. Well, f of 0 is 0, this is what I am given, and also that this is, well, I am also given that this integral -1 to 1 f of x dx, this is also 0. Then the theorem, the result says that the inverse transform, the inverse Legendre transform of the function f tilde of n by n times n plus 1 is given by this expression, is given by a minus integral 0 to x ds by 1 minus s square integral -1 to s f of t dt. Okay. So, what I have is the following expression here. So, this is, so I have to show that the Legendre transform inverse of my function f tilde, where f tilde is the Legendre transform, is given by this particular integral. Okay. So, the proof is as follows. So, I am given that R of f is, R inverse of f is h. So, it is given that R of h is f, right. So, I just rewrite this expression in the forward sense. So, R of h is f, and I can write this as, so R of h is the following. So, R of h is d dx, it is d dx of 1 minus x square times dh dx. So, that is my R of h, and this is also equal to f. So, by the definition of R, the operator R. Now, let us call this as my expression A. Well, I do not want to mess it up with this A. So, let me call this as I. Okay. So, I am going to integrate, my expression I, and I integrate I from -1 to x. I integrate I from -1 to x, and I see, let us see what happens. When I integrate, I get that the right hand side is integral from -1 to x f of t dt, and the left hand side is, we see that the integral 1 minus x square dh dx, and I have to evaluate this function at the limit x and at the limit -1, and of course, well, at -1 this quantity vanishes. Okay. So, I am left with this new expression. Okay. So, then let me call this as 2. So, then when I integrate again integrate 2 in the same range, in well, this time I am going to integrate with respect to, well, in the limit 0 to x, what I get is, I can immediately get my function h. I get that h of x is given by integral from 0 to x. So, a new dummy variable ds divided by 1 minus s square. So, I divide first and then integrate, which will bring in this this factor times integral negative 1 to s f of t dt minus a. So, that is the constant of integration. So, I see that f of h, it satisfies all my conditions given in result 1 in my theorem 1. So, then since this needs to be checked, and this is quite easy to check, that h x satisfies all assumptions that were listed in theorem 1. Okay. So, I see that h of x satisfies all assumptions listed in theorem 1, and I see that in so I can directly use my theorem 1 result to come to the conclusion that the Legendre transform of R of h of x is given by n times n plus 1 times the Legendre transform of h of x. Okay. Now, I have defined my h of x to be the R inverse of f. So, this is nothing but negative n times n plus 1 times the Legendre transform of R inverse of f. Okay. So, then let me just rewrite this expression here. So, what I have is the Legendre transform of R inverse of f is negative 1 by n into n plus 1. So, that is negative times the Legendre transform of f. Okay. So, then what I have is that the Legendre transform, well, I take the inverse now. I take the inverse in this expression, I get that R inverse of f, let me take this negative here. So, negative R inverse f, which is given to be the Legendre transform inverse of the Legendre transform of f divided by n into n plus 1 is given by negative h of x, which is nothing but our expression. Well, h was, we have shown that h is nothing but negative of negative a plus integral 0 to x ds by 1 minus s square integral from negative 1 to s f of s, well, f of t, let me just use the dummy variable t dt. Okay. And that brings us to the result of this theorem, which we started with. Okay. So, that brings us to the result. So, then I have one more result in the another theorem. I state it in the form of another theorem. It tells me that if I am given a function f which is continuous, in each sub interval of minus 1 to 1. So, it is piecewise continuous, and I define another continuous function. By g of x defined by the integral of f. So, g of x is nothing but the integral of f. I see that the theorem says that the Legendre transform of g prime of x is f, well, it is a Legendre transform of f. We can see that from the definition of g, and this is also equal to g of 1 minus integral from minus 1 to 1 g of x p n prime of x dx. Now, to show this result, it is quite the form of the result shows that we have to use integration by parts. So, I would rather leave this, the proof of this theorem, to the students to see that this is indeed the case. So, you need to use integration by parts to come to this conclusion given by the theorem. Okay. So, then let me state another result. Let me state a result again in the form of another theorem, namely the result on convolution of two Laplace, the convolution results on Legendre transform. So, it says that I am given the Legendre transform of two functions. So, if I am given that the transform of f is f tilde and the transform of g is g tilde, then I am given that the transform of f star g is the product of the two transforms, right. So, what I have is where my convolution in this case is defined in a specific manner. My convolution of f with g, I define it equal to h. This is nothing but 1 by pi integral from 0 to infinity. So, this is how I define my convolution of two function in the Legendre sense. So, integral 1 by pi integral 0 to pi f of cos mu sin mu d mu times integral 0 to pi g of cos lambda d beta, where my x is cos v and my cos. So, these are how I relate my variables. My cos lambda is the following variable, it is cos mu cos v plus sin mu sin v cos beta. Okay. So, then I am going to leave this theorem without proving and move on to the next result. So, this theorem will be useful in some cases, but you know, but not in a lot of problems. So, I am going to use this theorem whenever needed, but I am going to move ahead without giving the proof. So, let us look at one application of Legendre transforms. So, as I said earlier, Legendre transform has lot of applications in potential functions and in boundary value problems involving Laplacian. So, I am going to describe an example in a boundary value problem involving Laplacian. So, Laplace, namely a boundary value problem in Laplace equation. Okay, so, the problem says solve the Dirichlet problem. Solve the Dirichlet problem for the potential function. Solve the Dirichlet problem for the potential function u of r comma theta inside a unit sphere, given by inside a unit sphere, and the potential satisfies the following equation. It is the Laplacian in the r theta frame. So, note the way how I have written the Laplace equation. So, I have the regular Laplacian with respect to r, and then I use my transformed, I have already transformed my theta derivative. So, I use my x to be cos theta del x 1 minus x square del u del x, okay, is equal to 0, where r is from 0 to 1 and x is from -1 to 1. Note that I am solving the Dirichlet. So, the Dirichlet problem is the solution of the Laplace equation on a 2D surface. So, this is nothing but the Laplacian in 2D Laplacian. Okay. And I have already changed my theta variable to another variable x, so that I can recognize the use of Legendre polynomials or Legendre transforms, okay, in that fashion. So, let us look at the solution to this problem. Well, I also need to provide with the boundary condition. So, I have the boundary condition as follows. So, let me state the boundary condition. I am given that u at r equal to 1 for any value of x is given by this function f of x from -1 to 1. Okay. So, I see that. So, let me introduce right away, take the Legendre transform of, let me call this as 1. So, I am going to apply my Legendre transform to this equation with respect to the variable x, and I am going to use my result given in theorem 1, namely how to. So, this I can see that this particular expression here is r of u. So, I am going to use theorem 1. Okay. So, apply Legendre transform, to arrive at this following expression or the following ODE. I get the following ODE: r square del u tilde del r 2 plus 2 r del u tilde del r minus n into n plus 1 u tilde. This is also equal to 0. So, I have already used here in this particular part of my ODE, I have used my theorem 1, which gives the relation between the Legendre transform of the operator r of u with this constant sitting outside. I see that this is nothing but, and also so this is the equation. So, let me call this as 1 prime, and then my boundary condition is reduced to the following. I have that u tilde at 1 comma n. So, this is my transformed variable n is given by f tilde of n. Okay. So, I know that if I were to solve this ODE, so 1 prime has 2 roots. It is given by the following. So, one of the root is either r is r to the power n, we can check that it is indeed one of the root. Let me call this as u1, and the second root is r to the power minus n plus 1. Okay. So, those are the 2 roots, and also I know that solution is bounded. I know that the solution is bounded from r 0 to 1. So, if I were to take u2, the second solution, that would not be the case, right. So, what I get is, well, let me say that my first solution is a times. So, that is the most general form of the solution, and the second solution is b times something. So, a and b are the constants to be determined by the boundary condition here. So, using the boundedness of the solution, I get that u of r comma n is nothing but f tilde of n times r to the power n. So, this is a solution which is bounded in this domain, and it also satisfies my boundary condition. So, at r equal to 1, u tilde is f of n. So, then of course, the next step is apply inverse transform. Applying inverse transform, I see that I get the following result. I have that u of r comma n is the Legendre inverse transform of f tilde times r to the power n. So, that can be written in this following summation. This is summation n from 0 to infinity 2 to 2 n plus 1 by 2 times f tilde of n times r to the power n p n of x. Okay. So, r is from 0 to 1. Now, well, so that completes the solution to this problem, but before I end this example, I just also want to highlight that suppose I were to solve the problem, suppose I were to solve the complement of this problem, also known as the exterior Dirichlet problem, right. So, suppose I am given and I am asked to solve the exterior Dirichlet problem, that is I am asked to solve one in the domain r greater than 1. So, in that case I can see that from, well, all the steps will follow all the way up to 1 prime, but then when I get to this point where we have two roots, okay. So, when I have two roots, I see that only the second root is going to make sense in the range from r for r greater than 1, where the solution is going to be bounded at infinity. So, I am going to use u2, so u2 which is b times r to the power n minus n plus 1, and I can see that u2 is bounded when r goes to infinity. So, r equal to 0 is not in the domain, but r tending to infinity is. So, in the exterior Dirichlet problem I have to take this second function as my root, and then my solution u of r comma n, well, u of r comma x, my second solution u of r comma x is the inverse transform, let us say n from 0 to infinity, well, f tilde divided by r to the power n plus 1 times 2n plus 1 by 2 times p n of x d, well, that is it. So, this is for r greater than 1. So, that completes the discussion on Legendre transforms, and the students are also requested to see more examples, especially the handouts and the assignments that I am going to provide. Now, in the next lecture I am going to introduce yet another new transform known as the Z transform. So, people especially working in signal processing and in electronics and communications, they must have heard a little bit about Z transforms. The most unique part about Z transform is this is one of the few transforms which is defined as a discrete sum. So far I have only introduced transforms which are defined in terms of an integral. So, in the next lecture the Z transform which will be introduced, we will see that it is a discrete sum. So, thank you very much, thank you for listening.